Okay, so we start Gazebo, and then we can spawn the model with this file and this model, one.robot. There's a mistake here. And then we can see it here in Gazebo. And from the view menu, we can select joint or transparent or even reset camera, just to change the views and the properties that we can visualize. Now, of course, this is not very convenient because, as we said, we need to be able to change to the right directory in order to access that file. So if we want to do it from anywhere in the computer, we can always use a launch file to facilitate this. Another thing that we're going to do differently in this launch file is here, point number 1. Load the URDF first to the parameter server. Now, this is the first time we are doing this in class, I think. And this is a very, very important point. From now on, every time we have a URDF file, we're going to load it onto the parameter server first. And then we're going to spawn the robot, not from a file, but from the parameter. Yeah? Does anyone know the name of the parameter where we are going to save this file to? The name of the parameter. All parameters have names and then the values. Do you know the name of this parameter? Seems not. I will introduce it to you in a second. The second thing that we do, actually, this point number 2 can be flexible. Start Gazebo through Gazebo ROS. We can do that in the launch file now, or we can do it separately. In fact, your launch file right now does not have step number 2. That's okay. That means we need to start Gazebo manually right now. Later, we will put start Gazebo automatically in the launch file. Okay? And third, we're going to spawn the model to Gazebo from the parameter server. Okay? So let's, before we launch this one, let's take a look and see what's inside. We can do raw set, minimal robot description, minimal robot description.launch. Maximize the window. And then let's look at this line. First, we have the parameter tag. That means we're going to create a parameter. Then we need to give the name of the parameter. In terms of loading the URDF to the parameter server, we will always use this name as a standard, unless we have more than one robot. But if we only have one robot, we're going to use robot description. Okay? Then we need to give the value. Actually, there's a few commands you can use. Right now, we're going to use the command text file. This will give the value to this parameter based on this file. If we have any command that returns a value, we need to use the money sign and the parentheses, right? This one here. And we say find, which is like ROS package find. It's going to return the path of this package in your computer. Doesn't matter where you are. So it'd be home, username, ROS, Indigo, ROS workspace source, blah, 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 minimal robot description, and then the file name. Okay? That's the first thing that we do. And then let me do this. Let me comment this out because you don't have it right now. Comments strictly follow this format. Exclamation mark, dash, dash, space, and at the end, space, dash, dash. That's a comment. Okay? So that's not going to happen. Otherwise, here what we're going to do is we're going to take Gazebo ROS. This tag right here is let's include another launch file in this launch file. Yeah, and this launch file is in Gazebo ROS in the launch folder, and it's called emptyworld.launch. This file will start Gazebo with several arguments. Okay, actually our arguments can go here, but I don't include any to make it simple. And then we can do spawn the robot. In the launch file, we always need to have a node name. This name can be anything. Here we just say spawn URDF. The package is Gazebo ROS. This is spawn model. And then this tag here is very important. Arguments, equals, then exclamation marks all the way to the end. And inside of this thing, we can have many, many arguments. Or like, for example, here we don't say file anymore. We don't say file like we did before. We say param. We're going to load the file, we're going to load the model of the robot, not from the file, but from the parameter. What parameter? Robot description. Why? Because we created it up here. This is still URDF type, not SDF, and we still include model as one.robot. Okay? So that's what we're doing. Two things here. Save it. Okay. Let me close Gazebo one more time just to make it fresh. Yeah, we'll open an empty Gazebo here. Come back over here, and then we can say ROS launch. All right? And then starting and loading. Okay? Now that's nice. We can be anywhere in the computer, and it will do this. Yeah, if the model has already been loaded and you try it again, it'll say over here in Gazebo, spawn model failure, model one.robot already exists. So it doesn't do it again. It just cancels that service. Okay? All right, you should be trying that with me. Yeah, so you can get to see it, how it works. And again, from the view menu, you can see joints, you can see the frames, you can also see the center of mass, and you can see context. We're going to use that a little bit later. Now the center of mass for the whole thing appears like this, and it would be somewhere in the middle. And context is for collision, and apparently you can't see much here. Let me see. Sorry. The contact actually would be around here. Why doesn't it not show it right now? Maybe we need to add some collision elements to the URDF. I can't remember if we have collision elements here right now.
I think we have. This last time we did what?
Let me take a quick look.
First control, we cannot use the first attack.
Let's take a quick look. We do have the collision element. So I'm not sure about that. I'll have to think about why we cannot see the context yet. Now, if you want to check if the URDF file was loaded into the parameter server, we need to look at this parameter, robot description. Now, some of you, your memory may not be clear, but to check things in the ROS parameter server, we use the ROS param command, and here we can say list. Now, there's a lot of stuff here from Gazebo, right? But we need a robot description. Where is it? It's right here. Okay, robot description is right here. And how do we check this value? ROS param, no info, get, not the list, get. And then you give the name of the parameter. Give me the value of the parameter called robot description. Well, it's very long, right? It's the URDF file that you saw before. Yeah, it's that URDF file. It's in the parameter server. Okay? And from now on, we will always use the parameters robot description to look at the URDF file. Okay? All right. So we can say list and then robot description. And a few more things about Gazebo models. When we say let's load a cylinder, right? Actually, that model needs to exist somewhere in your computer. It's not just magic, right? There's a model for that, the way that it looks. And in Gazebo, all models are stored in the hidden file .gazebo. dot gazebo, don't forget the dot, in your home folder, in your username folder. Yeah? So again, you can say CD or just CD, and then you can say, hey, let me see gazebo, and it's right here. And then inside gazebo, you'll have another folder. In my case, it's modelsgazebosim.org, but it might have a slightly different name. Yeah, and you'll start to see that here there are many objects. And I probably have another folder with more objects over here. You can also use those models to insert them into your world via the insert menu. For example, I come over here, I click insert, and this menu will say, hey, in this folder, you have all these things, all these models. Yeah, for example, I can click on this one and move it anywhere and just click on it, and I can use these to resize them. Oh, you see those green lines? Those are the contacts. If I zoom in, you'll see blue dots on the floor, like this, and those are contacts. And the green line is the direction of the normal of the contact. The normal direction of the contact surface. Yeah. And you can introduce many things, including really advanced worlds. Let me see. For example, gas station. Yeah, you can introduce a really big thing like this. I forget the name of some of these words. You have ladders. You have all kinds of things. Office building. Yeah, you can create very advanced models, including water, air, mountains, anything like that. It's just models. You can find. You can put rovers, any kind of robot, right? Willow Garage is the office of the company that created PR2. You can put entire buildings inside. So it's very advanced and very powerful if you want to have enough time to create advanced models, whether robots or the world. Okay? And you can adjust all of those properties here. You have the models here. Yeah? Actually, you also have here the physics of the world. For example, gravity. Right now it's set at negative 9.8. Over here, you can, if I set it to 0 and take gravity away, maybe these models will start floating if there's a contact on them. Or maybe when we introduce them at the beginning. For example, let me try a submarine. Sinking, I cannot see it. Something happened. Okay, these are anyways, these are some examples, and you can also reset. Here actually nothing changes, but you can reset the world if things move. Okay. If it cannot find a model, it'll say something like this, unable to load this file for some reason. So there was a segmentation fault, and that's why my gazebo stopped working. I can start it again. So all of these are saved there, and more models can be inserted with this script. So right now, maybe some of you have not downloaded many models. Some of you have, some of you haven't. If you click on this link, it'll take you to a file. You can download it. It's a SH file. Then you run it, and it'll automatically save all the models into the Gazebo folder. Yeah. If you don't have these folders, what Gazebo tries to do is look for them online and the default website, and then try to download it and install it before you use it. But this may take a long time. Yeah, so you want to download them first to make sure you can load Gazebo quickly with a model. All right. Now, so once we insert our robot, yeah, we can also look at the Gazebo topics and Gazebo services. We want to be very familiar with these. So, for example, we can say ROS topic list, and we have things that are the link states. In our current robot, we have 2 links, right? And so the link states will be their position, their orientation. For example, we can say ROS topic echo Gazebo link states. And I can make it a little bit smaller. Yeah, but you can see you have the pose. Actually, it's showing you how many links you have. If you look at the top, it says name, ground plane link, 1DF robot link 1, 1DOF robot link 2. We have 3 links. For each of these 3 links, you're going to get a position and an orientation. So here's 1, 2, and 3. And then you're going to get a twist. Are they moving? Because they may be moving, right? So they have a linear velocity and an angular velocity, the 3 of them. Okay? Those are the link states. Then we have the model states. These are the actual models, like the cylinder or the ground. So let's take a look. Here at the top we see ground plane and 1 DOF robot. Those are the models. The floor and the robot, 2 models. Yeah, so here you see not the links themselves, but the actual models. And 1 robot counts as 1 model with its base frame of reference.
What's the W in orientation?
Oh, don't know.
Yeah.
Oh, come on. How many numbers in orientation?
Numbers?
Yeah. How many axes on this orientation? Not axes. 4 values represent the orientation. What is it? 4 values. Huh? Quaternion, yes. Quaternion. Some of you don't know what a quaternion is. Some of you studied it and have forgotten. If you don't know what a quaternion is, ask Tony. Then he has to go back and study, and then he can tell everyone what a quaternion is. Okay, what else do we have? And then we can also set the link state, so we can change them and move them around. We also have services, raw service list. Okay. Here we can apply a body wrench. We can also get joint properties or get link properties. Okay, but we need to say raw service call something something. We also we can spawn models, URDF models, SDF models. We can set joint and link properties. Yeah, so we can do both. Some of these through topics, some of these through services, and some of these through both. And a key topic here is Gazebo link states. So names, poses, and twists. We can do that. And coming up, we're going to start using these services to move. Actually, we moved some of these models before, right? Remember, we took the cube and moved it around to hit the cylinder? Or we were rotating. Maybe you didn't remember that, but from the previous class, we have a few commands from raw services that moved the parts. So look back. Now, section 3.5 is going to introduce a controller, a PID controller. A PID controller to control the joint that exists between the 2 links. Yeah, a PID controller to do position control on the actuator, and then command that joint to a particular angle, and then move the 2 links. So that actually means that we need to start connecting the URDF with Gazebo with ROS control. So we'll have a brief introduction to ROS control here today. So ROS and Gazebo work together to command the joint with reference angles. And we're also going to be able to read the displacement, the joint displacement, through an encoder. My friend, what is an encoder? Okay. Someone else, right here. What's your name, my friend?
Sri, we take the projector.
Sali, what's an encoder? It's right here, encoder. No? Very good. It's a sensor that tells us the position or the joint angle displacement, 0. Pi divided by 2. Something like that. It tells us the angle, okay? So, by integrating the controller, we can command the arm and we can read the angle. Two things. So we're going to use code. Actually, the first thing we're going to do is show you some code that might be able to do this without ROS control. But this is not the best choice. It's going to be a little bit slower. Then we're going to use ROS control to do this. So you're going to be able to see how we do it both ways. Okay? In this demo code, we'll have a PD controller that is found in the control hardware normally. Yeah, we're going to actually simulate that with ROS control and Gazebo later. For example, if you use Baxter has a PD controller in the control boards inside the robot. You just tell Baxter, move to this angle, and it does. It has a built-in PD joint controller. So PD joint controllers normally are running at a very low level in the robot. Could be the UR5 or the E1. Yeah? You can always build another PD controller on top of that one for a different purpose. But the robot itself will have a built-in PD controller at the very low level to control the joints. Here we're going to have a simulated PD controller. A little bit similar to what you did on homework 1. And then later we're going to use Gazebo plugin for controllers, so we don't do this manually. And this is going to be an example of what that plugin really does. But right now it's going to be slower because by doing this on the code, we have extra computation and bandwidth requirements. For example, serialization. What does serialization mean? When you publish a topic, you put data into the messages and then you publish them, right? That part there has some computation. It also slows you down. So this is extra compared to the plugin. And when you send the message over a ROS topic or a ROS service, there is some message latency. The message has to travel through the Wi-Fi or through the Ethernet cable. There's some latency there through the topics. Yeah. If it's on the same computer, and let me say that. And then the plugin doesn't have to do some of these things. It's a little bit faster. Right now we're sending things from the node to Gazebo, right? There's a communication route between the node and Gazebo. So this slows you down a little bit, very little, but it slows you down. When you use the plugin, it's faster because it doesn't do these things. Okay, let's look at this code. So it's a minimal joint controller. Source. Yeah, you can use ROS-SED. I'll use Emacs directly here. Minimal joint controller.cpp. Okay. Some new headers that we haven't seen before. These are gazebo messages. Get the state of the model. Yeah, where's the robot? Things like that. Apply joint effort if we want to move an arm. Get joint properties. And then this one is very important. Sensor messages joint state. This message here helps us to know the state of a joint. If you don't know what it does, what can you do? You open a terminal, right? Let me do this, and you can say, what? Cross message, show what? Sensor messages, joint state. You're going to get the joint angle position of every joint. It's an array, so if you have 6 joints, you hit 6 numbers, you get the joint angle velocity. And effort is something that can mean either force or torque. Why do we call it effort? Because we have 2 kinds of joints. What kind of joints can we have? Revolute and prismatic. Prismatic. If it's prismatic, it's linear, so you get a force. If it's revolute, you get a torque. So effort is a word that describes either one of these. Each joint has a string name, like shoulder 0, shoulder 1, elbow 0, elbow 1. And so these values correspond to the order of the names. Okay? And then you have your header. So that's what we're doing, okay, with sensor messages joint state. Here, we're going to have global parameters. Why are they global? They're at the top, yeah, above all functions, outside all functions. We're going to have a PID controller. So here's KP. Yeah, normally you're going to be a lot larger than KV. And then we need to say what's going to be the sampling rate for the controller. How often is this controller going to run? Right now, we're just saying 10 times per second. Okay? Then we have a saturation function. If you don't remember what saturation is, it means it's the limit of the actuator. We can have different kinds of saturations. We can have joint limit saturations. You can tell the robot, hey, move to back here, and then you can't move further. So you saturate the joint, but also it can be for the torque. The arm may need to apply more torque to carry a heavy object, but the motor cannot provide it. Yeah, it's not like it's infinitely powerful, right? It has a limit, and if you ask it to do more, it cannot. When it cannot do that, it saturates. Yeah. Let me skip this periodicity for now. And here we're going to have a command, position command callback. Okay. And we'll get to that. Let's go to main maybe first to see how this is working. Initialize the node, have node handle. We create a variable for duration of 0.5 seconds. We have this function called test services. This is just saying, let's make sure services are available before attempting to process anything else, right? We can go find it, test services. Okay, and the way we do this is always, this is one way to do it in C++. We use raw services and then the method called exists. It takes the service topic, in this case gazebo applying joint effort, yeah, and this is tell us if it's running true. So if it's not running, we issue a warning, and then this returns false. Then we do it again, not just with joint effort, but joint properties. Yeah, and then we say services are ready. Okay, so we're just checking if services exist. Who's running the services? Gazebo is. Okay, you're running Gazebo, you're checking, is this happening? Now, why do we do spin once? Where these will serve for the callbacks to get some value that might be needed for those calls. And then we sleep half a second to give it some time. And then this is just to test. After we know that the service is running on Gazebo, we proceed to create our client. Okay? So this is set the torque client. If we want to move the arm, then we can issue a torque. Yeah, this is going to be our object. We take the node handle and say service client. We give the type of the service topic, Gazebo messages, apply join effort. Then we give the service topic right here. Okay, so that creates our object, service client. We do the same thing for get joint state. Yeah, we have a different type and we have a different topic. Now that we have these two clients, the clients are used to do what? To make a call, right? And when we make a call, we send a service message with it. Remember that the service message has two sides, the request and the response. Yeah? So here for the set torque client, we need to issue an effort. We're going to command an effort to the joint. You should move with this kind of torque. And then when we send a torque to the joint, it's going to move. When it moves, we want to know the position. So we get the joint state through the service message. All right? So we create these as Gazebo messages right here. We also have 1, 2, 3, 4 publishers. Torque publisher, velocity publisher, position publisher, joint state publisher. And all of these, in the first three, we're going to send float 64s. And the last one, sensor messages, joint state. Okay, these are our topics, joint torque, joint velocity, joint position. We have one subscriber, position subscriber, and this goes into the position command topic, and this has a callback. Tell us the position. So what we're doing here is actually we're going to communicate with Gazebo in two ways. One way is through services, another way is through topics. For these messages, we're going to have these types, torque message, position message, which is Q1. Q's are normally used to describe joint angles. And then Q1 dot is the velocity, the joint angle velocity message. Okay, these are part of what we're going to send out in the topics. Then we have local versions of that, Q1, Q1 dot, Q1 error, because we need a controller, yeah, and torque command. We have joint state message, we have a duration of 0.01 seconds, and the rate is 1 over that. Okay, so now we go back to the service messages to fill them up. Here we created these, now we're going to start filling them up. So we have effort command service message, the request part, and then we need to give a joint name, and we're going to say we're going to work on joint 1. We only have one joint in this model. And then we're going to set, let's set the effort to 0. So this is just local, nothing happens. And then do that for this duration, yeah, that we set above, 0.5 seconds, I believe. And then for the joint state, the request is also joint name. And then we go to the messages we'll use in the topics. Here's joint state message, header, stamp, time now. And then we need a name. The name is the name of the joint. It can be a vector, so we can use pushback, but we push back a string. We only have one. And we set the position and the velocity to 0. Now we're going to go into the while loop, and this is where we have the controller. Okay, see how this works. The very first thing that we do is we're going to issue a service call from the get joint state client. And we send this message that we created above, yeah? And so it's going to return the response. It's going to return the response. We can get that right immediately. Get joint state service message dot response dot position. Here the 0 is redundant because we only have 1. So you can, I believe you can do this without the 0 here. And we save that to Q1. And then we're just going to, just to show you that you can do this, we're going to republish this onto a topic. So you take Q1, you take Q1 message.data, this is just a number, you save it here, and then you take that to the position publisher, say publish, and send it in. So you get it and you send it back. What's my angle? And send it back. Yeah, so here, Gazebo is not going to do anything. We're going to do the same thing with the angular velocity, Q1 dot. You get, in the response, you're also going to get that thing, rate 0 here, that's the velocity, and then you save it back into Q1.message, and then you take the velocity publisher to publish that. Okay, now, right here we're getting the state through the service call. Now we can get the state, we're going to publish the state through the topic. So we have Q1, and we have Q1 dot. We save that to joint state message position, joint state message velocity, and then you publish. Right now we're just showing you a few different ways to send things to Gazebo. Okay? Now let's look at the controller. Here you want to compute the joint angle error. How do you do that? Well, you have a goal position command, something where you want to move. This command, I think, is at the top. Let me search for it. This one here. Right now is 0. Goal position command. Yeah? Let me see, 1 second. And the callback, we're going to get the latest position of the robot. The latest, the current position of the robot. But then we set that value to the goal. So maybe the robot is at 0. You get that position. And then you set the value 0 to the goal. So it's not moving. Yeah, it's not moving when this goal is 0. So here, this is the current position. And then Q1 is where the robot arm is. So the error here should be 0. This function is looking for something periodicity. You can look at that later, but we save the error here. And then this error is multiplied by Kp, and then we subtract the derivative of Q1 dot. Now these controllers, there's a bunch of different ways you can do this. Here we're not computing the error of the velocity, we just pass the derivative of the velocity. And then this is going to be a command. Okay? And that command is then set to this publisher. Guys, pay attention. There's a lot of detail, and a lot of you are already lost, right? So, need to ask questions and focus. And then we publish this again. We can also send this through the service. We have the request and set the effort part of this request to torque command. Yeah. If you don't know what this looks like, remember you can say ROS SRV, show, Gazebo messages, apply effort. Yeah, and then you can see the response and the request type for that service. And then we take that set torque client.call with that message and send it out. Here, if you want to make sure the service call was successful, you can look at response.success, save it here, and then use a test. If the result was not successful, make a warning. We have a subscriber and the position command. So we want to spin once. Get the position for the subscriber, run the while loop again, get the subscription, get the position from the subscriber, run the loop again, get the position from the subscriber, run the loop again. That's what spin once is doing. Get one message, try again. Get one message, try again. Okay, and then we have sleep. All right. So we examined the code. This is a summary. And let's then do some manual steps to understand more how Gazebo works, how the code works, and then we'll run it in a second. So here, it's important for you to learn the joint properties in our 2 degree of freedom simulation. Let's do that through the service. We can call Gazebo's get joint properties service, but we need to provide the name. And what this does is, this service actually is being constantly called in the control loop to get the position and the velocity in the code. Okay, don't get lost. We are controlling the joint, right?
Yes.
And we want to get the position of the joint angle position, and the joint angle velocity. Okay, so here's Gazebo. It's there, right? And then we want to do this service call. So you can say raw service call, Gazebo, get, joint properties. But then we need the joint name. Joint 1, yeah? Like this. And so it says the type of joint that it is, revolute, no damping, the position is 0, the angular velocity is 0. I can successfully get this information, and then the message got the properties. Okay? So that's what we're doing inside the code. We can also issue joint torque commands using the apply joint effort service with joint name. First, let's get some information about this. Raw service info, Gazebo, apply joint effort. So this says actually the service that is running this is Gazebo, and it uses a type of Gazebo messages apply joint effort. Okay, it needs a joint name, it needs an effort, it needs a start time, and it needs a duration. This thing needs 4 things. Here we can also say raw service show Gazebo messages apply joint effort. Okay, so here's the name, here's the effort, here's the start time, here's the duration, and it'll say whether or not it succeeded.
Success is the request or the response.
You tell me.
I think it's the response.
It's always a response. Request is the first.
Sometimes I read the book, it's the request. I think the sequence of the request and the response can be changed.
No, it's fixed.
It's fixed.
You always have request first, and then you have response. It never changes. Yeah. So in the PD control loop, we're passing a joint torque update to the effort field of the effort command service message. Okay? We're doing that in a while loop all the time. Sending a new torque command. Go here, go here, go here, go here, go here. Whatever that is. So now what we're going to do right now is manually send a command message to the torque of the joint to move it. Okay? We can do that. This is not a torque. Now we're gonna show you how to send a desired angle. A desired angle manually. Okay. So we're gonna say Rust topic pub position command. That's the topic. Standard messages float 64 1.0. Okay. Later in the program. I think we haven't run the code yet, so this is not going to work if we do this right now. We haven't started the node. What we're going to do is also examine the dynamic response. Do you remember what dynamic response means? Well, the answer is right there. We want to know how the position changes, how the velocity changes, and how the torque changes for that joint. How do we do that? RQT plot. It's going to help us plot data from any topic. So we're going to be able to say RQT plot all of these guys. But remember that these are ROS standard messages. So they have the data element. We don't just look at the joint position topic, because that topic has a data element inside. Joint position data, joint velocity data, joint torque data. Okay, so let me see. I think we need to start this node. Yeah. Let me see this topic list. Let's run. I forgot to include this command in our slides. Minimal joint bus run minimal. Yeah, so I started that node. Okay. Now we need to publish the topic. Oh, before we do that, let's do RQT plot. So you can say RQT plot now, and actually let's do a ROS topic list so you can see them. ROS topic list. So here's joint position, joint torque, joint velocity, right? It's waiting. So we say ROS RQT plot joint position data, joint velocity data, joint torque data. We're going to wait for a second. So here's our curve. Nothing is changing right now, right? So we put this here. Actually, let me put it here. And then we open one new window, and then we're going to do the ROS topic pub. ROS topic pub position command standard messages float 64 1.0. We can just say 1.0 here. Yeah. That's the dynamic response, okay? And actually, if we pause this and we maximize this, you can see that the joint position is the blue line. You can see how it goes up, right? It's not, well, it has a smooth response here, and then the velocity goes up, and then it needs to slow down again as it's arriving, and the torque goes up very much so, and then you need to stop so it goes the other way, and then stabilizes at this level. This is the torque that you need to maintain that position, and it needs to work against gravity. So it's not free. When you do this, there's a muscle working there to keep the position. Yeah, it's a torque that you need to keep for that position. So it's very nice, right? You have the node listening for topics. That comes in, goes into the controller, it does a error computation, it updates the torque command. Yeah. It computes the torque command, and then it begins to move the arm by sending the effort. This would be great for you guys to go back and use GDB on this with Emacs or any IDE you want to use, and go line by line after you publish the command. Yeah, to see how this is working. So we do that, you get something like this, right? Now, we want to now also study contact dynamics. What if I hit something? What if there's an obstacle? We're going to hit a table in a second. So right now, we're going to manually insert a coffee table under the robot using the insert menu. And then we're going to do the same thing and study the response. So let's, actually let me go back to this window and go back to Gazebo. And let me publish again, but with 0 as a position. Now, let's move this a little bit. And let's say insert. Actually, it's here. Let's look for a coffee table. Yeah. Put it right here. So it should be able to hit it. We take RQT plot. Maybe we'll put it down here. Play it. Yeah, everything is normal again. And then send this again. See if it hits. Oh, that's okay. That's okay. Let's see if we can do. Okay, there it is. So, for example, we can zoom in on this. Yeah, and for the position, it never reached 2 here, right? Never reached 2. I was unable to do that. The velocity was cut off very quickly. Didn't have a chance to slow down like it did before. And then the joint torque, well, had a big strike here when it struck the coffee table. Yeah. So that's the dynamic response. You need to make sense of these responses from the physical events. Okay, now we're going to do the same thing, but we're going to use the plug-in. That means we don't have a node running a PD controller anymore. So this is a more advanced way of running a controller. Gazebo plugins by default, now you can change this, can run at full rate in the Gazebo simulator. At least for Gazebo 2, that's considered 1 kilohertz. And here we don't publish anything. It's running directly in the plugin. Do you know what a plugin is? It's a library that can be loaded dynamically. Yeah, so it's going to be a .so file, but it works within the Gazebo ecosystem. So Gazebo loads these libraries into Gazebo. Okay? Now, we're going to also use ROS control and ROS controllers. These are packages, ROS control and ROS controllers. So ROS controllers in Gazebo have interfaces that are identical to the actual hardware. These packages are designed to make controllers work the same in simulators and in hardware and expand them. So the dynamic behavior in simulation would be similar to the hardware. Okay? Not exactly the same, but similar. However, and ROS control and ROS controllers were designed to be general and extensible, but they're complicated. They're not that simple to manage. And then in page 130, you can see that they depend on other packages that you need to download. Now, if you use the script in this book to install the packages, you have already downloaded those dependencies. But you can refer to this page to look for more. Here's a link, ROS control, joint controllers with Gazebo for reference. And right now what we're going to need to do is do 5 steps to set the ROS joint controller as a plugin in Gazebo. Number 1, in the URDF file, we need to include limits for 2 things, the joints and the torques. Otherwise, this plugin will not work. In the URDF file, we need to say for every joint that we have, what are the limits of that joint? Normally, you would have that information available from the manufacturer. Also the torque limits. Then you need a field or a block, a transmission block for each joint. For example, if you have 6 joints, you'll have 6 transmission blocks for each joint. The transmission is something about how does motion from the actuator translate into the link. Because we normally use gears or harmonic drives, and there's a transmission ratio from one to the other. Yeah, when the motor moves like this, maybe the arm moves like this. So we need to encode that transmission ratio. For these examples, we're going to use a value of 1. But again, your manufacturer would tell you what that number is. Then we need a Gazebo block. And this Gazebo block we tell what plugin we're going to use. For now, we're going to use the plugin called libgazebo ROS control. This is the plugin that we use for PID control of a joint. For your homework, you're going to use a different plugin to control a mobile robot with 2 wheels. It's called a differential drive plugin. Then, because we're using a controller is a PID controller. There are some values that we need to set. What are those? The PID gains, and in case of the integral term, the I, we also have something called clamping values, the maximum and the minimum clamping values. So for each joint, we need to set these values. And for that, we need a YAML file, Y-A-M-L, YAML file. And then we need a launch file where we set everything up. Number 1, we load the controller parameters from the file into the ROS parameter server. And then we use one of the packages from ROS control to start the controller. Let's look at the details. So now in this file, minimal robot description with joint control.urdf, we're going to have 3 new blocks and we're going to study that. So let's take a look at this file, and we're going to look at the joint block with the limits, the transmission block, and the gazebo block. Let me maximize this window. ROS set. Actually, we're right here. So, oh no, ROS CD, minimal robot description, Emacs, and minimal robot description with joint control.urdf. I have an alias that puts color into this. Actually, sorry, it just opens in this window quickly, like that. So let's take a look. Here's our normal link. Here's the link block. Here's our normal collision as before. A collision block, visual block, inertial block. And then we have link 2, finishes here. And then down here for our joint, we have joint 1, type revolute. We have the parent, the child, the origin, and the axis as before, but look, now we have limits. And these limits for the effort will be set to 10 Newton meters. Yeah, this is torques. These are the position limits, the lower position joint angle and the upper position joint angle in radians, and the velocity limit, radians per second. Radians per second. How many? The angular velocity in radians per second. So it cannot move faster than this. That's our joint block. And then here we have the transmission block.
What's the dynamics thing?
Oh, damping. Yeah, sorry, I forgot that. So damping is related to the friction of the joint. Something about the friction of the joint. It slows the joint down. Because joints have friction, right? So there's something working against the motion of the joint. And this number acts to slow you down. In your homework, you will change this value around to study the response of the robot with different values. But it's something that dampens the motion. It slows down the motion. The bigger this number is, the harder it is to move. Yeah, that's a friction component. Of course, none of these are easy to find perfectly, right? It needs experimentation to know these values. A lot of physics behind this. Then here's a transmission block. We have a name, and then we have a type and a hardware interface. For now, ROS control only has one type and one hardware interface, I think, implemented. So this would always stay the same. It's a simple transmission, and it's an effort joint interface. It's like you send a torque, and it returns a joint angle. Yeah. and we have the name of the joint upon which this transmission is working. Transmissions work with actuators, the actual motor. Yeah. So here you can create a name simple like this, motor 1, effort joint interface, and this is the gear reduction. So this number is something that a manufacturer would tell you. It's depending on the connection of the joint and the actuator. Yeah, like again, a motor might move just a little bit, but the arm might move a lot more, depending on that reduction. And finally, we have the gazebo block, and this is where we say the plugin. We give it a name, Gazebo ROS Control, but the name is this one right here. When you download the binaries for Gazebo, sudo apt-get install, ROS Indigo, ROS Control, this will get installed in OPT share. Yeah, so it's going to be able to find it. And then this robot namespace is very important. Look at this namespace right here. This namespace is designed to give a name to your robot. Yeah, so anytime you are publishing or subscribing from Gazebo, it'll say one DOF robot at first for different things. You'll see how it works. But this namespace is very important. You'll need it in your controller parameter file. This is the name of your robot namespace. And you'll also need it in the launch file. Write that down. No one is taking notes. Yeah, I'm going to emphasize that later here, but it's important. Okay, so if we want Gazebo to work with the plugin, we need to add these three things, right? For every joint. When we use Baxter, you'll see that this is repeated 7 times for each arm, and also for the head, and also for the hands. Okay, so the files get quite a bit bigger. And like I said, this namespace name is very important. Now let's look at this controller parameter YAML file. If we go back to minimal description, yeah, normally in every package, this is just for example, but in every package you'll have a folder called config. In this case you called it control config, but normally it's going to be config. And inside the config folder, you're always going to have YAML files. YAML files are files that contain data for parameters. Last time in our launch file, we saw how we set one file to robot description, right? But that's just one parameter. What if you want to load 15 parameters? You don't want to do that one by one. You can do that putting those 15 parameters in one file and then just loading one file. Let's look at this file. One DOF control parameters. YAML. So look at how this file starts with the robot namespace, okay? With the robot namespace. Where did we put this name? Oh guys, come on, I just emphasized it. This name is in the Gazebo block.
Yeah.
Robot namespace. Yeah, I just told you this namespace is very important. It's going to go into the controller param file, and then I show you that file, and you were like, okay. Now here we have 2 comments: publish the joint states, and then something about position controllers. Remember, a controller always has 2 parts. One is the feedback, the joint states. What is the state of my joint? The positions, the velocities, and the torques. And then there's always the command or the reference. Where do I want you to go? So here, these names are important. We'll see them in a second. Joint state controller. This is the name of the controller for joint states. And we need to give the type. Joint state controller, joint state controller. And here, what we do is say we have a rate of 50. For position controllers, we use this name, joint 1, position controller. And then we have the type, effort controllers, joint position controller. We have a joint name, and then we have the PID values. This value is hard to set. You normally want to start without it. You might have a value of 0 there. If this is a value of 0, this can be 0, and this is 0. But if you have a value here, then you need a minimum and a maximum clamp. Because you may not know a lot about PID, but when you use the integral term, the error can accumulate so much that actually it hurts you when there's a over accumulation of error. So you need a maximum and a minimum limit. Okay? And so we have a controller for each joint. We need to say the type, the name, the PID gains, and the limits. Tuning PID gains is challenging in general, and in ROS, an easy way, the best way to do it is by using RQT reconfigure. We haven't studied RQT reconfigure yet. There's a link here, but it's how to change parameters online. So you change the p-value, and you tell the robot to move in the simulator, and you see the response, change it again, until you get something that is more stable. Okay? By default, the libgazebo plugin will have an interface with RQT reconfigure, so you can use that easily. Now, how do we get this started? Number one, the controller files need to be loaded to the parameter server. We're going to do this in this launch file. The launch file will load the YAML config file to the parameter server. These are parameters that are used by the joint controller later. The joint controller, where is it? Where is the joint controller? No, those are the parameters, the PID parameters, and some types. Where is the controller running? The PID controller, where is it running? Yes, and the plugin. Yeah, the plugin will be set to load these values in the way that we set them in this file very specifically. After that, we load the robot URDF to the parameter server, robot description. Start Gazebo, spawn the robot into Gazebo by using the model in the parameter server, and start the controller plugin by using the controller manager package and the spawner node. This is new for you. So there's a package called controller manager. Yeah? And then when we spawn the node using this namespace, the same one from the Gazebo block, it will then start the controller. It will look for the types of controllers that we defined, and then it will start doing the PID control. Let's take a look at the launch file. Oh, no, that's the name. Minimal robot with control. Oh, it's still not good. Okay, so let's see. So we load the joint controller configurations from the YAML file to the parameter server. Yeah, so we say ROS param. But ROS param is different from param that we used before. ROS param is a tag that looks for YAML files. YAML files. So when you use ROS param, you need to give it a file with a YAML extension. Got it? So we say, what's the file? We need to give it the path, find, minimal robot description, control config 1.control parameters.yaml. Command equals load. So this whole thing here is going to load all these parameters. Number 2, let's load the URDF into the parameter server, into the parameter called robot description. So here's the file with join control.urdf. Goes into the parameter server. Now here we are not opening Gazebo by ourselves. We can include that line easily. So we'll start Gazebo first, then we will run this launch file. So we say Gazebo ROS, spawn model, arguments, parameter server, robot description parameter, URDF type, model, 1.robot. Oh, here it is. Here we start Gazebo. Maybe yours doesn't have this. Maybe I changed this at home recently to make it easier. But you can start Gazebo first and then run this one.
Okay.
Yeah. This will start Gazebo. And then we're going to start up the controller plugin via the controller manager. So we give it a name, controller spawner, package, very important, controller manager, the type, spawner. Respawn means if something fails, do you want to try again? And here we're saying, no, we don't want to try again. Output equals screen. This means any ROS info messages. If you want them to show up in the terminal, then you need to say output equals screen. This is when we say ROS info, ROS warn. In order for them to show up on the screen using a launch file, we need to say output equals screen. Namespace, very important. The namespace from the Gazebo block. Yeah? And then arguments. These arguments are the names of the controllers that we used in the controller param YAML file. For example, let me see. I'll show you in a second. But this is join state controller and join one position controller. Do you remember these names? No? From the YAML file. Let me change to that. Control config. Control parameters. See this name? Join state controller. Join one position controller. You see these two names? Those are the arguments here. Join state controller. Join one position controller. Yes or no? Here. The name of the controller. The name of the controller. Those names are created by you. And then you need to pass those as controller names. Sometimes we will have position controllers, velocity controllers, effort controllers. And sometimes you'll have them for each joint. So Baxter has 7, right? So you need to put a list of 7 controllers, maybe plus the joint state. Yeah? This list can get very long. You can compare this to Baxter files. For those of you that have some experience, to see how this looks for a more complicated robot. All right, so we'll close this, and we'll close Gazebo. Okay, and we'll close this RQT file. We'll close this topic, and I think that's it. So now we can try to launch this file. So let me let me do one thing real quick. Oh, I did comment this out. Yeah, that's important because we want to do it separately. Okay, so the first thing I'm going to do is, let me close these windows for now. Close this one and close this one. Make this one small. Well, let me see. Let's start Gazebo first. Okay, here's Gazebo coming up. I'll minimize this. And here we're going to launch the launch file. ROS launch, minimal robot description. And let's look at the output that comes from these messages, okay? The output is important for you guys. Okay, so here, loading Gazebo ROS control plugin. Yeah, loading the plugin. As soon as we had that from the launch file. Then, after you load, starting Gazebo ROS control plugin in namespace 1DOF robot. Okay? So you load it and then you start it. Gazebo ROS control plugin is waiting for model URDF and parameter robot description on the ROS parameter server. And we provided that and then loaded Gazebo ROS control. That's what's going to control the robot. Then down here, we have controller spawner, waiting for server, controller manager, load controller. Yeah, that's what we just used to launch the plugin. Waiting, and then loaded controller, join state controller. Loading controller, join one position controller. Now, yeah, loaded controllers, this one and this one. And after you load the controllers, you can start them. So right now they are working. Okay, they are working. So now in Gazebo we have this, but we have these controllers running, right? And we can go back. Let me maximize this empty window. And we can say ROS service list. Now look at all these new services with one DOF robot. And they're followed by controller manager for the most part, except this one. Join one position controller PID set parameters. So if you want, you can have a service that changes the PID values. Yeah, but that's why RQT reconfigure works, because it's actually sending values to this service right here. And you do it automatically. Right now we have to do it manually if we use this directly. We have list controllers. So for example, we could call this and get a list of the controllers. I think we can just do this. I just say raw service call and call the service topic, and it says, hey, let me tell you what controllers you have. Join state controller, join one position controller. It's running. Here's the type. This type comes from our configuration file. Here's the type. Here's the hardware interface. And here's the resources. Okay. So I just called it. It's a service to list the controllers. And then if you want to load controllers, you need to give the name of the controller. Because sometimes, let's say we have position, velocity, and effort controllers. Sometimes you'll say, I want to use position. So you load them and start them. Or actually, there's another thing called switch, which you can see here. You may be in position and you say, I want to switch to a velocity controller. When you switch, you stop the previous controller, unload it, load the new controller, and start it. That's how ROS control works. This is about ROS control. Okay? Now, I haven't shown you the picture yet. In last week's Gazebo presentation that I sent you as an additional PDF, there I have explanation of ROS control with Gazebo. So if you've studied that, you might be more aware of what's going on. My sense is you have not looked at it, because a lot of you look very confused. When I give you something, please try to look at it. Otherwise, you get behind. Yeah? I know it's a lot of material. This is not an easy part of ROS. Okay, so this is what we have here. We can also look at the ROS topic lists, and you might get a different list. Joint 1 position controller command. This is where we're going to send the joint angle command. Yeah, like we did before, but this topic is coming from the plugin, not from ourselves. Okay, we have two topics for PID, parameter updates, descriptions, and then this is joint 1 state, and then this is joint states. They're a little bit different, both of them. The joint 1 state will give you the position, velocity, and effort. The joint states will give you position, velocity, and effort for all the joints. But the joint 1 position controller state, that will give you information about the PID gains. These are both state, right? And they have the word joint, but what's the difference? This one has controller. So you get information about the controller, PID, values, things like that. This one gives you position, velocity, effort for all joints. Yeah, we can take a look. These are topics, right? So we come back here. We can say ROS topic list. Okay. Here's joint 1 state. So we can say ROS topic what? Echo. Let's do it just one time, not many times. Number 1, number of times to do that. We do this. So here's PID and the clamp, time step, error, process value, set point, and everything related to the controller, the goal, the error, and the parameters. If I use joint states, and by the way, this is for one joint. If we have more than one joint, actually this is for joint 1. If we have more joints, we get more topics like this one. Joint 1, joint 2, joint 3, or whatever name we use for that. If we do the same thing for joint states, you get the name of the joint and then position, velocity, and effort. Okay? So now what we're going to do, as before, is examine the dynamic response. We're going to use RQT plot like before, but now look, we need to go to the namespace, joint states, position 0, velocity 0, effort 0. Yeah, a little bit longer. And then we can command to join 1 position controller command, and then we'll see this response, okay? So let's see how this works. Let's move this over here. Zoom in a little bit. Let's bring out our message over here, our terminal. So here, RQT plot, yeah. RQT plot, let me see, that's a long name. 1.DOF robot joint states.
F or 0 means like average?
Yes. Like that. Let me copy this and paste. Velocity 0 and effort. Okay. If there's an error, it won't show you, but this loaded okay. Yeah, let's minimize that window a little bit. Maybe put it around here. And let me change windows. I need to open a new one. And then we're gonna launch, right? Oh no, make the manual command. ROS topic pub, 1.DOF robot joint. No, what is it? Need to look here. Rate of 10, joint 1 position controller. What is it? Why doesn't it? Joint 1 Precision controller, command 1.0, and we'll do this at a rate of 10. Okay, ready? And look at how it's moving. Why is that? PID control. Yeah, so actually here you can choose the zoom in version, but zoom out. Actually, I don't, let me try this again. Let it run. Let's make this small. Let's send this back to 0 and back to 1. I want you to see the full response one more time. So it goes back. And then back to 1. Slow PID response, right? That means it's a bad controller. That means the gains are not tuned properly. That's what that means. So we get this response right here. We can zoom in into it. Yeah, we have something like this. Position is blue, so goes up, goes down, goes up, goes down. Yeah, that's a very bad controller. There's a lot of oscillation. You want something that goes kind of in a straight line to the set point. And then the velocity will have the same response, and the effort also has this variation. So it doesn't reach the set point quickly and stay there. We could increase the P and the D parameters to try to improve the response. Yep, this is about control. Okay, but we won't describe this in detail for now. All right, so I'll close this and kill the rest. But what have we done now? We have integrated a controller through the libgazebo ROS control plugin. URDF, Gazebo, ROS control together. Okay, and this is a great way to do things. Okay, that's the end of this section, and then let me introduce you to your homework for today. You can work on this now for the next couple of hours. I can help you if you need help, and you can explore more things. So let's look at your homework. Okay, so the goal for this week is to learn about SDF and URDF and how to integrate them with Gazebo and ROS control. And you will follow a few tutorials along with section 3.7 and 3.8 for building more difficult models and controllers. Okay, you need to send me a PDF file with answers and screenshots to your questions. I ask you when I need a screenshot from you. Okay. And then don't forget to include title, name, ID, and divide the document into 3 sections that are part of this homework. There's section A, B, and C. Okay, so your homework also keep the same format and submit under this 3 name. So here I say open this tutorial from the Gazebo website, and you will follow that. It'll open in a second. But here I say, show me the RViz shot. Now, so far we haven't worked with RViz in our class yet, but we're coming to that next week. And show a screenshot. Here you need to give me an answer. You need to write it in English. Yeah, you need to study and you need to write some sentences. So far, I don't think I've asked you to write down answers for me. Just do things. But in this homework, you need to write a lot. I want you just to study. There's a lot of studying part here, and you need to know what sacrofiles are. Show me Gazebo. But here I just have more questions for you. More questions. I'm asking you change some values in the URDF file, look at the dynamic response, and then tell me what you see. Okay, dynamic damping, inertia, rotation of inertia values, things like that. Then one tutorial on ROS control. So questions about transmission block, plug-in, loading and switching controllers, things like that. And finally, section C is building a mobile robot model. Yeah, this is section 3.7 and 8 of the book. You're going to use a mobile robot with 2 wheels. Look at the URDF, make it more and more and more complicated. And then use a plug-in for that, do the controllers, do all that stuff for something that's more complicated. Okay, so that's going to be this part. And you can see how many points each section is, okay? So you have pretty clear my expectations for you. So that's the homework. So next 2 hours is designed for what? Not for me to keep lecturing. It's time for you to practice. So you can use this time to start the homework or to ask me questions about last week or anything like that. This is time to stay here, talk, share, practice, code, try things together, okay? We'll do that for 2 hours. Thank you.
I think, can you explain the